everyone, it's me, Carolyn, and today we are going to, or in this video, we are going to talk about section 5.5, which deals with how do we determine how many ways something can be done. So, for example, when we were flipping a coin 3 times, how many different outcomes would we have? If we flipped a coin twice and then drew a card a couple of times, how many different ways could we do that? Because a lot of times with probability, we need to determine our numerators, how many ways in the sample set that we're looking at, and then the bottom number is how many total ways the experiment can happen. So in this video, we're going to be looking at some of the other ways we can do that besides just listing them all. So I'm going to share my screen to our guided notes that I've kind of typed up for you. And I want to start off with an example of, let's say we have a person who is going to be getting dressed. And they have 3 pairs of shoes, 5 pairs of pants, and 11 tops. And if everything kind of looks okay together, how many different outfits? And these outfits are going to be a pair of shoes, a pair of pants, and a top. Okay, so one of each. And we could, if we wanted to, and I'm going to start drawing this tree because here you are. And let's say you put on your pants first. So from each, here we'd have 5 different choices for our pants. Okay. From each of those, we would have 11 tops. So I'm not gonna be able to get them all in here, but imagine 11 tops from each of those pieces. And then from each of these, we have our 3 shoes. If you think about how many different outfits we'd have, we'd have 5, but then we'd have 5 groups of 11, which is actually 55. So 5 groups of 11, that's multiplication. And then from there, we would multiply our pants together, our shoes on there. So we could get our answer by taking 5 times 11 times the 3, which if I dragged out my calculator here, 5 times 11 times our 3, we get 165 different outfits. All right, and that's where this kind of leads to this multiplication rule of counting. And it says if we have a task, okay, which is a sequence of choices that we have to make, and there's P of the first choice, Q of the second, and R of the third, and so on, the way we can put them together, so like this case, pants and tops and shoes, notice my word and, we have these multiplication. So let's do some examples and I'll kind of walk through how I work through these problems. All right, we have a zip code. How many zip codes can we make if it first of all consists of 5 digits? And we can't start with the number 0, but we can repeat them. So what I like to do is I kind of put my choices here. We have a 5-digit zip code. So there are my 5 choices. I have to have the first spot, the second, the third, and so on. So I kind of say, okay, how many ways can I do that first choice? Well, if it's a digit, digits go 0 through 9. So there are 10 different digits, but I can't start with the 0. So I only have 9 choices for that first spot. Here I can use any digit that I want and I can repeat. So I could use the one that was here as well. So I have 10 choices here. And again, we can repeat. So the 10 and our 10 and our 10, because we have no restrictions on those other places. And then the multiplication rule says we just need to multiply those together. So okay. What would have happened if we could not repeat? Let's do this one again, but this time not allow us to repeat. Same thing, we can't start with the 0. So here we only have 9 choices. Here we'd have 10 to start, but we can't use this one, so we only have our 9 choices. Here we can't use either of those 2, so we only have 8 choices, and then 7, and then 6. So again, multiplying these together, we have 27 to 16. So a lot less choices when we are not allowed to repeat. All right, let's do one more here. We have a 7-character password that can be created from the alphabet if we don't allow for repetition or capital letters. So we have 7 characters. 1, 2, 3, 4, 5, 6, 7. And here we want, you have to remember that there are 26 letters in the alphabet. Sometimes that's one of those things you knew, but sometimes slips off the top of your head. So we do have 26 letters in our alphabet. There are other alphabets that have more or less. And we are going to create something that does not allow for repetition. So in this first spot, we have 26 choices. But once I've chosen this one, I can't use that letter again. So it's 25, and then 24, 23, and 22. And again, every time we choose a letter, we're down 1 value. Forgot my multiplication symbols up here. And our multiplication rule says, since we want to have this and that and that and that and that, we are going to multiply those together. And doing so, takes me a little while on my calculator here. I have 3, 3, 1, 5, 3, 1, 2, 0, 0, 0. So a lot of different passwords that we could come up with. So just imagine what would happen if we allowed for characters, capital letters, and so on. So we have, I mean, this is a large number, but that would become even larger. In some of the formulas that we'll see that can do this without having to multiply all those pieces together, we're going to have something in it called a factorial. First of all, we denote our factorial with some sort of integer, so a positive integer followed by this exclamation point. The way it is defined is for, in general, n factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down until we hit 3, 2, 1. So for example, 6 factorial, and that's how we would read it, as 6 factorial, is equal to 6 times 5 times 4 times 3 times 2 times 1, which is 720. I did the work ahead of time. Luckily for us, when we get larger values, we don't have to necessarily go into the calculator and type all those in. A lot of calculators nowadays do have the factorial button on them. So I'm going to show you where mine is. Okay, the first thing I'm going to do is type in the number 14. And now what I need to do is get that factorial button. Mine is hidden under this PRB. So PRB does stand for probability. So I'm going to hit that button. And you'll see I had this little NPR, this little NCR. We will get to those later today. And then we have this exclamation point. So I'm going to arrow over till I get that exclamation point. I'm going to hit my equal button. And now you'll see the 14 with the exclamation point in there. And if I hit equals again, we actually get the value. Now I want to notice here that we do have this little 10 here, and we have this 8 point something. So this is a really large number. I'm going to put in what I see. And then that really means times 10 to the 10th power. Scientific notation tells us that we would actually move this decimal place 10 times that exponent over. So we'd have that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need to add 2 zeros, if I remember correctly. 3, 6, 9, 10. There we go. So that would be our actual value. A lot of calculators will go into the scientific mode or the scientific notation mode because these values are too large to show on your screen. So I don't have enough character spaces to show it on my screen. So it has to go into that scientific notation. Now, does that mean there's really 2 zeros? Again, we don't know for sure because this piece could have been rounded. One thing we have to do to make sure that everything works is we had to define what 0 factorial was. Because in some of our problems, we will get a 0 factorial pop up in the formulas. And to make it all work, 0 factorial is defined to be the number 1. So in other words, it is equal to 1. We couldn't really start at that point and go down till we got to 1 because 0 is below 1. So we define it to be 1. You can use Excel for factorials. There is a factorial function. I'm not actually going to go to Excel and show you here, but it is located. If you go into that drop-down menu again for the functions, under the math and trig category. And unlike the statistical category, it's in our math and trig, and it is the FACT. Okay. Where we are going to use it or see that factorial show up is something called a permutation, or a little bit later, a combination. And a permutation is a way of finding, taking n things and picking r of them and placing them in an order. So we have n distinct different objects, and we're going to take r of them and put them in an order. So here the order is kind of important. The other thing that's important is we do not allow for repetition. We will talk about, I'm not going to talk about repetition. Then things get a little bit more complicated, and we would do like what we did with our passcodes and things like that. That's the only way to kind of do them. We don't have nice little formulas that pop up when we allow for repetition. The formula for a permutation, and I'm going to zoom in here a little bit because it does look a little small, is this little, first of all, the notation. We put the n, and then we put the letter P to stand for permutation, and we're going to have the R. So again, n is the number of objects we have totally. R is how many we are picking to put into an order. And the formula is taking n factorial over n minus r factorial. Okay, so I'm going to go through our password example when we did the alphabet. So we have the alphabet, right? Which was 26 letters. So those are the things we're choosing from. We're choosing from all of those 26 letters. We are going to be picking 7 of them to order, right? And we didn't allow for repetition. We could have, that would have been a different problem, but we didn't allow for repetition. So this is a classic example of taking 26 things and ordering 7 of them. So this in our notation is a 26P7. According to our formula, it would be 26 factorial, which is a really, really large number, over 26 minus 7 factorial. Again, you could calculate this, but you'll notice when we went to that PRB button on my calculator, we had this little symbol show up. So I like to use my tools. Why not use the tools that you have in front of you? So I'm going to do this 26P7. I just kind of finished this out here. I'll do it both ways. So 26 minus 7 is 19. Okay. I also, before I do that, I kind of want to show you it's the same thing we had done before. So I want to think this is what, 26 times 25, 20, 24, 23, 22, 21, 20, and then 19 all the way down, right? This one is 19 all the way down. These pieces, oops, I forgot 20 in there. Oh, this is 20. Those pieces would cancel, and I'd have that 1, 2, 3, 4, 5, 6, 7 piece that we had before. So we should get the same value. So we could go this route. So, but I'm going to show you how to use that button on your calculators if you have it. So for my calculator, I need to type in the 26 first. Let me turn it on. 26 first. Then I go into my PRB button. Sorry, PRB stands for probability. And I want my P and PR. So I'm going to grab that button. So I'm going to hit the equals. You'll see it show up. 26. And then we want to put in the 7. And we'll hit our equal button. And we get that 3, 3, 1, 5, 3, 1, 2, and then 3 zeros, which is exactly what we had the time before. All right, a combination. Very similar because we have n distinct objects and we're going to pick 5 of them, but this time we're going to just throw them in a pile. We're not going to order them at all. We're just going to pick them and put them in the little pile or a group or just have them clustered together. We're not going to arrange them in some ordering. So basically, this is our notation. Again, it's at n, and we use a C for combination. So again, this is no order, no ordering. And basically what we're going to do is take our permutation. So take what we had up here, and we're going to take out all the different orderings of one value. So if we had one specific password, and we rearranged all those numbers, this is how many of those different rearrangements we would have had. So in the formula, it is going to be that n factorial. We have r factorial, n minus r factorial. Okay, let's do a couple examples. And I will be using my button on my calculator to do the NPR or the NCR and kind of work with it. So let's say we had a person who's got 15 different books and they want to read them. And they want to take 5 and read those 5. And to them, the order is important. Or maybe they want to order them on a shelf and put these 5 different things on a shelf or display them in something. So we have 15 things and we're going to order 5 of them. So since we are ordering them, this is a permutation. And we had a total of 15 objects, which we are picking 5 to order. And then going to my calculator, again, 15, get my P, which is the first one, and then type in the 5, hit my equal button again. I get 360,360. All right, now we have our 15 books, and we're going to take 4 of them on vacation. So the order in which I throw them in the suitcase really doesn't matter. We're just going to take 4 different books on vacation. So the ordering does not matter. So this is a combination of 15 things, choosing 5 choosing 4, sorry. We're taking 4 books on vacation. So here we're going to do the 15 first. Then we'll hit that PRB button. I go over to my combination, that NCR. Hit my equal button to get it showing on my screen. Type in my 4, hit my equal button again, and I got 1365. So there are 1365 different ways we could choose 4 books to take on vacation. All right, how are you guys doing? Hopefully we're doing all right. So let's do some more examples here. I am going to kind of go off script a little bit after I do this example. And look at, first of all, this one we're looking at an activity that consists of 8 men and 11 women. Okay, and we want to know how many 5-person committees we can make. Okay, so we don't care if they're men or women on this committee. We don't care if you were chosen first or second. We just are either concerned that you're on the committee, you're not on the committee. So this is kind of like taking our total group and picking 5 of them, not ordering these 5 people. So this is a combination. Since we're not making any what's the word I'm looking for? We're not making any male-female restrictions. We're going to lump all of our people together. So we had 19 total people, and we're going to be choosing 5 of them for this committee. We're going to lump them all together. And I'm going to do just this one. And from now on, I'm just going to leave it in that combination or permutation form. So 19, I'm going to find that value, hit my NCR button, then type in my 5, and we come up with 11628. All right, this next piece, how many ways can we choose a president, a vice president, a secretary, and a snack coordinator? So we've got 4 different roles here. And now the role does make a difference, like who is president versus who is secretary makes a difference. So the order in which we place these people matters. Sometimes it isn't how we order them, but how we rearranged it. So another way to think of it is if I took the 2 of these people and switched them, would it make a difference? In my 5-person committee, if I took Sally and Jane and they are both on the committee and I just switched them in where they sat, does that change my committee at all? No. If Sally and Sarah are president and secretary and I switch those 2 around, does that make a difference? In that case, it would because of their roles of president and so forth. So here is, again, we have no gender specifications. So again, we're going to be taking that 19 people and we're going to 1, 2, 3, 4 assign 4 different positions. All right, let's step it up. This gets a little bit more complicated. How many 5-person committees can be formed containing 3 men and 2 women? Okay, and we're going to do this in 2 separate pieces. So we need to be specific here. We've got men and we've got women. So how many ways can we choose 3 men? Again, we're just picking them to be on a committee. So we had 8 men and we are choosing 3 of them to be on this committee. So that's the number of ways we can order or group these 3 men. We also have 11 women and we are going to choose 2 of them. Okay, think of this as the going back to the beginning of this video where we talked about we have tasks, and we have 2 tasks. We have to choose our men and we have to choose our women. Since these are, we can then use that multiplication rule. Since we're doing this and that, we would multiply those 2 together. So this one I'm actually going to carry all the way through because we do want to multiply those. So we have that 8C3. And a lot of times it's easiest just to get those values, write them down. Or depending on your calculator, which may be a little bit more advanced than mine, to get our pieces. Okay, so there we go. That we have 3, 30, 80. And this was our 5-person committees. Notice it's a few less because we're taking out all the other possibilities. Okay, what if instead of saying how many, I asked what is the probability that a 5-person committee has 3 men and 2 women? So we're talking about a probability now. So thinking back to the beginning of our chapter, probability is a number of ways that can happen out of the total number of ways. So the number of ways we could have 3 men and 2 women, we just found in that piece here. And the total number of 5-person committees was the number we found up here. And again, we would probably want to reduce this, or we could go to a decimal, and so on. So making sure that you do go through that final step. All right, let's do one more before I switch gears a little bit. I want to do a different problem. What is the probability that a 5-person committee has a majority of women? Okay, majority would be 3 or more, right? So 3 women, 4 women, or all 5 women. So again, we're looking for probability, and it is a 5-person committee. So this is going to be our bottom piece. But now we got to create on top those majority of women committees. All right, so let's do our 3 women here. Whoops, 3 women. That means we'd have our 11 women. We need 3 of them, but that's not a complete committee. We still have 2 other people. So we have to make sure that those 2 people are men. So we have that. And again, we would multiply those 2 pieces together because we have the 3 women and the 2 men. We could have a 4 women committee. That would be 11C4. Whoops, that's a C. C4, and we still need our 1 man. So and we could have 5 women. 11C5. We could do an 8C0 if you wanted to. That number will turn out to be 1 because there's only one way to choose no men. Okay, but we have to do something with these pieces. So we have a 3 woman. We can't have and a 4 woman. It would be or, because either a 3 or 4 or a 5. These have nothing in common. So going way back to being disjoint probabilities, we would add them together. Or you hear yourself saying the word or. And again, out of our 11,625, which was that total number of ways we could have a 5-person committee. Now, when we get these probabilities, just to make sure you're not making mistakes, remember the rules for probability. Probability has to be between 0 and 1. If you find out you have something that's negative, you made a mistake somewhere. If you have something that turns out to be bigger than 1, you made a mistake somewhere. So go back and double check. Okay, I want to go back and talk about kind of some of the problems you would have seen in the previous sections before I come back and finish this, in which you can do this technique or you can do something that you may have learned before. So let's say we have an order comes in with 85 discs. Okay, so 85 discs. I don't know what these discs are. They might be a CD or a flash drive or something. And unbeknownst to us, there are 5 which are defective. Okay, what we're going to do is we're going to test 2. We test 2 of them. If both are good, we will keep the order. Okay, what is the probability? We keep the order. Okay, and I'm going to do this one using some techniques. First of all, from 5.4, where we were talking about conditional probabilities. And then I'm also going to do one using our combinations and permutations, and you'll see that it is exactly the same thing. Okay, so we're going to keep the order, which means the only way we kept the order was both of them that we tested were good. So we have 85 total discs, 5 are defective, which means we have 80 good ones. Okay, since we're going to check it, the probability that we're checking 2, so there's my 2 that I'm thinking about. The first one is good. So the probability that the first one is good is going to be 80 out of that 85. Then we're going to test another one. Now realize we're not going to test the same one we tested, so we're not going to put it back in. So the probability that the second one is good is going to be our 79 because we got a good one the first time out of the 84. Okay, so we would have this value here. And I'm going to go through another way to do it. I mean, we can get our decimal here. We should probably do that, but I'm going to actually just show you mathematically, for those of you that are interested, that the way using combinations and permutations will turn out to be the same. All right, so that was one method, kind of using the techniques in that conditional probability from 8.4. If we use combinations and permutations, again, we're just picking two of them to test. It doesn't matter which one we're testing first. So we're going to make sure that we're keeping this is going to be, well, we have 80 good ones, right? And we are choosing two of those two to be the ones that we get lucky enough to test. Out of all 85, choosing two pieces. All right. So I'm going to kind of go and get our formulas that we had. This would be 80 factorial over 2 factorial times 80 minus 2 factorial. You're going to see me do some math here for those of you that like that. 85 factorial over 2 factorial, and then 85 minus 2 factorial. Okay, when we divide fractions, we flip and multiply. So this is going to give me that 80 factorial, 2 factorial, this would be 78 factorial, times flipping this one, 2 factorial would be 83 factorial over 5 factorial. Okay. I'm going to get rid of the stuff that's obviously the same. And now I'm going to start writing some of the different pieces. Okay, looking here, just the first one, that's going to be like 80 times 79 times 78 all the way down, right? This is 78 all the way down. Those 78 pieces cancel, leaving with just the 80 and the 79. Here we'd have that 83, which is 83 all the way down. This one is 85 times 84. 83 all the way down, 83 all the way down. Those cancel. We're left with that 80 times our 79 over the 85 times the 84, which is exactly what we had before. So two different ways to think about it, getting the same result. And a lot of times these probability methods are interrelated. So just kind of realize that there may be a different way to view it, but it still is good. All right. So we're going to finish off this section about talking about what happens if some things aren't quite distinct. Both our combinations and our permutations rely on the fact that we have distinct items. So what happens if they aren't? Can we still work with them? The answer to that is yes. And for example, let's say we take the word, I like the word Mississippi because it has a lot of different repetitions of letters. And I want to know how many different words. Now, when I say a word, it's just putting the letters in a different way to get a different look, okay, if we use all of the letters. So for example, if I switched this I with this I, you wouldn't be able to tell. It would still be the same word. But if I switched my M and my I around, it would be different than what I have beginning. So that's what I mean by different words. Okay. The way we do that is what we have to do is kind of take out rearranging those I's. How many ways can I rearrange the I's and not really notice a difference. So, I mean, if there was a distinction, like this is I number 1, I number 2, I number 3, and I number 4, rearranging, how many ways can I rearrange those I's? How many ways can I rearrange those S's? So we have to take that out, take those repetitions out. And the way to do that is we're going to start with that n factorial. This is an n factorial. So that's the total number of letters that we're starting with. And here is us taking out or dividing out all the repetitions. So if we have M of one kind, P of another kind, and so forth. So for our Mississippi example, we have 1, 2, 3, 4, 5, 6, 7, whoops, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different letters. So we could just rearrange them, 11 factorial, but some of them look the same. So we had 1, 2, 3, 4 I's. That means I want to take out the 4 factorial repetitions of the I's. We had 1, 2, 3, 4 S's. These are multiplied together. And we have 2 P's. So if I do this division, that would tell us how many different words we have. Leaving them in, we could have 11 factorial different words, but the I's, you wouldn't be able to tell the different ways of manipulating Mississippi and it still look like Mississippi. So this is how we can kind of get rid of that indistinctness. Okay. This kind of concludes chapter 5. There are more complicated ideas out there. So for example, you can go in other places. We'll look at poker hands. Those tend to be a little bit more difficult. I'm not going to cover them because they are kind of tricky. They're worse than the male-female, having 3 men, 2 women, or having a majority of women kind of problems. So they are difficult. And for this class that I'm teaching, we aren't going to need that level of difficulty. So this concludes chapter 5. From here, we'll be going in looking at more complicated probabilities and how we work with them. But that's in the next few chapters. So I will see you in the next video.